Okay, hi everybody. We're going to get started with the last two sessions of the day. I think there are still some people coming in from outside, but we're going to get rolling. Okay, so I'm happy to introduce groups 6 and 7. So yeah, I guess without further ado, take it away, Sofia.
Thank you. Good afternoon, everyone. Thank you all for being here, especially as half of the crowd has left. I want to start by just asking, how are you all feeling energized? Please give me a woo if you are. That's what I wanted to hear. Amazing. So far in this conference, we've heard about solutions for the energy transition, including policies, including technology development and financial viability. However, we may have heard just little about droughts, illegal mining, wildfires, and deforestation. There's a current environmental and social problems happening during the energy transition, and unfortunately, they are often overlooked. If you were here for the keynote talk by Sir David King, you understand what I'm talking about. In some cases, it is possible to mitigate this impact. Other times, we must adapt and must endure the energy transition to environments aggravated by climate change. Our team will take you through different areas of research on social and environmental impacts, as we use the Sustainable Development Goals to illustrate the different areas covered. Without further ado, please welcome our first presenter, Danny.
Thank you, Sofia, and good afternoon, everyone. Today, I'll be presenting my thesis research on the development of a tool to estimate the greenhouse gas emissions, as well as the decarbonization performance for oil production. The thesis starts with the background that even though the development of renewable energy, as well as carbon sequestration technologies is in full force right now, the crude oil still have to supply 30% of our primary energy demand, which translates to heavy environmental costs, which according to the IEA contribute to around 9% of energy-related emissions. However, the existing study put less emphasis on the crude oil productions, often overlooked by the highly carbon-intensive end-use consumption of oil derivatives. So in this project, I aim to build a detailed bottom-up life cycle assessment model, as well as equipping it with the decarbonization measures to assess its opportunities. The development of the models, the key steps of developing the models are the first two ones. So the first one is to identify the processes and equipments as detailed and as high resolution as possible, and then integrating it with the production characteristic as well as the development plan of the oil production platform. Those two steps will then guide us on calculating the environmental flows in terms of energy, material consumption, as well as emissions to the environment. And then those environmental flows could be aggregated depending on how they are being released to the atmosphere, either directly through the fuel assembly or as a product of gas flaring. In the end, we will then present the environmental impact as carbon intensity in the unit of gram CO2 equivalent per 1 megajoule of crude oil delivered to the refinery. And in the end, we will then assess 5 different decarbonization scenarios and see how much it can reduce the carbon intensity from such production. The developed model will then use on a case study using data from a soon-to-be developed offshore crude oil platform in the offshore Nigeria. So the graph on the left presents the forecasted oil as well as water production, and on top of that, the platform is expected to produce around 2,500 cubic feet of associated natural gas per barrel of oil produced. Our development model will give the graph on the top right which illustrates how the carbon intensity from the same production facilities will differ across its lifetime, starting a little bit high at the beginning because of the construction, as well as the exploration of the field, and kind of plateau around the center where the production establishes. And then it will increase again as the production efficiency decreases. This model comes with a lot of uncertainty regarding the input parameters. So the Monte Carlo analysis was done to assess how it propagates toward the end of the result, which is represented by the line graph, which outline the 90% confidence interval of the carbon intensity estimation. The same set of analysis also outlines that the flaring efficiency and emergency venting intensity are the two most important input parameters that affect the carbon intensity of oil production, because it highly relates to the proportion of the carbon dioxide and the methane that is being released via the field. As already mentioned before, that this model also assesses different sets of decarbonization measures. So in the baseline scenario, scenario 1, we assume that this source is being used to power all the equipment, as well as the associated natural gases being flared to the atmosphere. Two of the most interesting results are scenario 4, where we can reduce the emissions from the crude oil facility significantly by 72% by actually putting the flaring and venting to zero and recirculating those natural gas to improve production. And the most optimistic scenarios is scenario 20, where all of the 5 identified decarbonization measures are applied concurrently. So there will be no natural gas or minimum flaring, and as well as equipping the production platform with carbon capture and storage, co-production of hydrogen, as well as equiping the production platform with renewable energy, as well as considering the different part of end of life for the production platform, which in this case the best results given by reusing those platforms for future projects. So to summarize, the key findings of these results are the crude oil, the upstream crude oil carbon intensity is dominated by the production, so the preliminary processing of the produced oil and gas, and the carbon intensity varies over time as the production behavior changes. And in the end, as we can see from the emission reduction measures, that the decarbonization of oil industry rely heavily on the technology of carbon sequestration, as well as the development of renewable energy, which also comes with its unique impacts on the environment. A portion of it that will be addressed by the next speaker, Sofia.
Thank you, Danny. We have heard a lot about lithium batteries in this conference, right? But have you ever thought about the impact of lithium? My project aims to answer this question by doing an environmental assessment on the production process of lithium from brines in South America using a life cycle assessment. It follows the Sustainable Development Goal, responsible production and consumption. So there is a region in South America called the Lithium Triangle. Well, it's not called, but it's referred to as the Lithium Triangle. It's between Chile, Bolivia, and Argentina. This region is extremely important because it holds over 50% of the world's lithium resources. So, however, it only accounts for 29% of the current world's lithium production. So, it currently has 5 active sites. However, there are over 15 sites that are under development and upcoming. So, this area what we see here in the Lithium Triangle, brine is found as lithium is found as brine in salt flats, which is found in high altitudes and very arid regions that are very scarce of water. So it is very important. So it is extremely important to assess the environmental impact of lithium production in this region because it's set to increase. And it also is, each brine composition, different brine from different salars is different. And it's extremely important to assess the impact of each of these sites as it requires a bespoke production process. So the aim of my project is to create a cradle-to-gate life cycle assessment, following the British standards of life cycle assessments, LCAs, using the functional unit of 1 kilogram of battery-grade lithium carbonate. Lithium carbonate is battery-grade lithium carbonate is what is used in the synthesis of cathodes in lithium-ion batteries. So the site selected is Salar de Maricunga in Chile. This site was selected as it's going to be Chile's third production plant, and there's not enough literature about its production process, its environmental impact of the production process. Therefore, a life cycle inventory was created, and it is what you see in this picture. So all of these processes were modeled, accounting for the material inputs, water, and energy inputs. I'll just run through this process a bit quickly. So first, brine is pumped from the aquifer in the salar, then it's pumped from the aquifer to the surface, and then it's pumped again to the shallow solar evaporation ponds for its concentration. Then it goes through an extensive salt removal process where calcium and magnesium ions are removed through 5 different crystallization processes. Boron is also present in the brine, so a solvent extraction process is used to remove it. Last but not least, this lithium carbonate plant. We have another calcium magnesium ion removal process, where then it goes through an ion exchange process for further purification and removing all impurities. And last but not least, it goes through a carbonization where lithium chloride present in the brine reacts with sodium carbonate and produce lithium carbonate. Once it has been dried and everything, we get what is called battery grade lithium carbonate with a purity of 99.5%. So there is a clear, obvious thing that we can see in this image, and it's that one process requires more water than anything else. So, and this process is the ion exchange process. So the total consumption of water to produce 1 kilogram of lithium carbonate battery grade is 1.5 meters cubed. I can tell you this, but do you know how much that is? It accounts for, let's say, 17 average showers of 9 minutes each. So 1 meter cube in this very arid region in South America is not the same as 1 meter cubed in the UK. So to put that into perspective, there is what is called a water scarcity factor. So the water consumption that actually is demanded from the land is equal to 120 meters cubed of water. So that means that we went from requiring 17 showers to 1,500 showers. So yes. So then multiply this number by 15,000 tons of lithium carbonate that the site produces a year for 20 years. So with this, I want to say that yes, lithium production in South America has an impact in local and water resources, affecting local communities and as well the native Chilean flamingo population that literature has highlighted, that has been has been disturbed due to mining in this area. Therefore, it is extremely important to quantify the impact of upcoming lithium production plants, and it is essential to make informed decisions and avoid terrible consequences for the people and the area in this region. Thank you so much, and now let me introduce Adit, who's going to explain the impact of lithium applications. Thank you.
Good afternoon, everyone. My name is Adit. Now, following Sofia discussion on the lithium production, now I want to tell you more about one of the most important application in the lithium, which is lithium-ion batteries. Plenty of my colleagues already told you about what is the use of the lithium-ion batteries, what is the advantage of the lithium-ion batteries, but what haven't still not said is about what is the hidden problems in the lithium-ion batteries. To produce the lithium-ion batteries, it creates a high amount of CO2. The material that they use in the lithium-ion batteries also use a material that have a minimum availability in the earth crust. Also, during the mining operation of that material is causing a socio-economic issue. Therefore, some researchers try to find what the new technology to solve these problems, and it's called post-lithium-ion batteries, or PLIBs. So the aim of PLIBs is to use more abundant materials or more safer technologies by using salt, sulfur, or even solid-state batteries. So these studies will aim to compare the environmental impact and also the criticality impact of the lithium-ion batteries and also the post-lithium-ion batteries. With the total batteries to be assessed is 11 that are consist of 3 lithium-ion batteries, 4 sodium-ion batteries, 3 lithium-sulfur batteries, and 1 solid-state batteries. First, on the environmental impact, we are going to assess with life cycle assessment, where we are going to investigate the carbon emission during the production of 1 kilowatt-hour of each cells. Then we do the criticality assessment, where we assess 9 indicators, and then we further group into 3. First, the geopolitical issue. Second is the market dynamics that related to supply and demand, and the last one is on the mining capacity. This will assess for all of the materials that we will use in the batteries. So here is the result of the environmental impact. Currently, none of the post-lithium-ion batteries is having a better environmental impact compared to the current lithium-ion battery. This due to the anodes that usually use in the lithium-ion battery that use graphite. It's been replaced to use lithium, which have a higher energy density by 10 times. But the amount of CO2 that produce when using lithium compared to graphite, it pollutes 1,100 times more than graphite. And also in the solid state and in the lithium sulfur, on the anode and also the electrolyte, it uses a lot of lithium in it. So that's why plenty of the post-lithium-ion batteries is having a higher environmental impact compared to the current lithium-ion batteries. For the criticality assessment, here 5 out of 9 indicators is showing that cobalt is having the highest criticality impact. It is because cobalt is related to low infrastructure that's related to illegal mining and some also involving child labor in it, where lithium is mostly due to the supply and demand that currently do not match, and nickel is mostly due to the mining reserve capacity. When we aggregate all of this data into the batteries, currently some of the post-lithium-ion batteries such as sodium and solid-state batteries is having a better criticality compared to the lithium-ion battery itself. When we see on the lithium-ion batteries, on the NMC 811, when we use 8 times more nickel compared to cobalt, it shows that the cobalt that highlighted in purple is having a similar criticality compared to nickel, even though it's 8 times lesser. So it shows that cobalt is having a high criticality value, even when it's very low when we use it. And on the lithium sulfur battery, it's having a lot of red in it. It's because of lithium. And again, it's mostly due to the use of lithium in the anode and also on the electrolyte in the lithium sulfur battery. Here, I also assess some of the materials like sodium, manganese, aluminum, or even hard coal that is shown in black, but none of here it shows. It's because all of this material is having a lower criticality impact compared to the all like nickel, graphite, copper, and cobalt. So the key message here is currently, even though post-lithium-ion batteries is supposed to have lower environmental impact currently, but currently none of the post-lithium-ion batteries having a lesser environmental impact compared to the current lithium-ion batteries. And for most of the post-lithium-ion batteries that, like sodium and solid-state batteries, they have a better criticality impact compared to the current lithium-ion batteries. And if we deeper goes into each materials, lithium and cobalt is being the hotspot in the environmental impact and also in the criticality assessment. And after we're talking about the carbon emission reduction on the batteries, now my friend Miguel will tell you more about the more carbon dioxide removal.
Thank you, Alex. I will be discussing my research on carbon dioxide removal development and policy design with a case study of Kenya. Now, for those of you who are unfamiliar with carbon dioxide removal, or CDR, this is the process in which CO2 is actively removed from the atmosphere and still permanently stored afterwards. Now, the picture on the left depicts the role of CDR in IPC mitigation strategies, with CDR accounting for the negative emissions seen in yellow. Moreover, the IPC has since put out global stocktakes on the right, which are holistic reviews that draw solutions from both global and national decarbonization strategies for subsequent agenda setting and implementation. Now, similarly, the CDR scientific community has set forward CDR global stocktakes, which are used for consultation for decision makers to set CDR-specific national targets. This thesis reviews the value of CDR global stocktakes in order to understand their intentions and implications, and qualitatively examines the motivations and needs of innovators in order to address gaps that may be inadvertently overlooked by supranational organizations. Now, the CDR space has been characterized in literature through its political economy, which reflects the interplay between market forces and political systems, its market-driven nature with corporations and private investors running ahead of policy and regulation, and finally, its information asymmetries, which hinder effective policymaking and further fragmenting the sector and limiting systemic visibility. Now, Kenya stands out as an emerging CDR hub in the future due to its enabling geology, its 93% renewable grid, and finally, an agriculturally driven economy, which all paved the way for both local and foreign innovators to establish their respective ventures. Methodology-wise, I utilized a social technical transitions lens and used a multi-level perspective framework in which I categorized the state of CDR report as a global stocktake up top in my landscape level. I atomized onto CDR ventures at the niche level on the bottom, and in between, in my regime level, I designated the Kenyan jurisdiction. So I had pressures from both the top and the bottom acting on the jurisdiction. After this, I conducted a meta study to evaluate the existing CDR frameworks within the field, and which were then used to assess the most robust frameworks for my Kenyan case study. Finally, qualitative interviews were conducted with Kenyan stakeholders to understand motivations and needs and map out socio-technical challenges and opportunities. Now, moving on to my results. On the left, I have the results of my meta study with all the frameworks, which reveal that only a limited few number of frameworks are broad and applicable to every single project out there. And as you can see, most of them concentrate on the bottom in the niche level with limited understanding of the whole space. So they don't really give you a good idea of industry, technologies, culture, or the government side of things. Now, the visual on the right reflects the findings of the same meta study onto the contents of the State of CDR report, our global stocktake. And this showcases a resounding priority of the stocktake for technological, economic, and CDR discrete policy dimensions, but heavily neglects other dimensions like ethical and social, impact, and finally management dimensions. Now, atomizing onto the two most robust frameworks, the one on the left reveals a subjective perspective from CDR Ventures. One, denoting the need for stronger governance and more policy, elevated policy direction. Two, the dependence on agricultural influences and latching onto existing supply chains. Three, the required levels of investment and the risk associated in order to scale. Four, their need to strengthen public perception in order to build a fruitful carbon economy. And finally, five, their respective roles in driving climate impact-related jobs for local employment. Complementary, the second evaluation framework on the right revealed a more objective perspective, denoting the venture's strong removal efficiencies, environmental management, and business model viability. However, challenges still remain in social equity and community engagement, and a low performance on their institutional dimension, as shown, requires the need for tailored policymaking and better integration of local contexts to ensure the sector's success. The thesis resulted in 3 key work products. The Kenyan case study revealed that there is a need for CDR global stocktakes to stress that their contents adhere to local economic structures in relation to the availability of resources and their market conditions. Moreover, there is a need to integrate non-CDR discrete policy into these global stocktakes in order to find synergies between CDR and other sustainable development goals. Finally, the meta-study revealed that there is a need to standardize evaluation frameworks in order to ensure universal applicability and representation of underrepresented regions. Thank you very much for listening. Now, my friend Ade will talk about the adaptive role of mini-grids.
Thank you, Miguel. Hello, everyone. My name is Ade, and I'll be presenting my research on modeling mini-grids for irrigation. And this addresses energy on clean energy and food security. Now, despite the growth in clean energy transition across the world, over 570 million people in sub-Saharan Africa still lack access to electricity. And this is focused in the rural areas. In the case study country Tanzania, less than 50% of the population have access to electricity. Therefore, solar-powered mini-grids, which are localized systems that generate and distribute electricity, have been proposed as a means to increase rural electrification. However, the deployment is hindered by high costs, low electricity demand, and limited incomes in rural households. On the other hand, agriculture, which constitutes 70% of rural income, faces low irrigation level and high reliance on rainfall, which is worrisome, particularly in the context of climate change and droughts. Therefore, incorporating irrigation loads into mini-grids has been proposed as a strategy to increase their viability by boosting electricity demand while reducing the income of electricity, while simultaneously increasing farmer yield and income. This study looks at finding the optimal conditions to incorporate these loads into mini-grids, considering types of crops, their seasonality, and timing of irrigation demand. The research uses 4 steps. The first step was geospatial analysis to determine the site selection, considering areas without access to electricity and the types of crops grown. Next was load modeling for the community size load. Third was irrigation and energy modeling to determine the size of demand and also optimize energy system. Finally, a fusion was done using Clover to determine the size of the photovoltaic module and battery storage capacity that can deliver reliable electricity at the lowest possible cost, which is represented by the levelized cost of this electricity. Now, 3 case study sites were used. Now, what do the results tell us? First of all, adding irrigation loads, contrary to expectations, without any form of optimization, decreases the asset utilization. Now, the graph shows adding irrigation loads. Also, the faded line shows mini-grid size for only community residential loads. Now, consistently, the months of May to October have lower utilization. This is because during that period, it's a dry season, fewer crops are planted, and it's also higher tiller output. As a result, LCE was almost double the reference scenario. So what could be done? The next option was to change the timing of demand. So by coordinating the irrigation loads with solar output, so irrigating in the afternoons compared to typical patterns that do morning and evening. So on average, this decreased the LCE by 10% for coordinated loads compared to uncoordinated loads. However, this was still higher than the baseline cost, the baseline LCE for mini grids for only residential loads. So what else could be done? The next option was to see if you could have an optimal crop mix for irrigation based on the crops, in the current region, so in terms of percentages. So by optimizing the crop mix, prioritizing crops that have a longer growth length, leading to less variation during the year. So doing this actually reduced the LCE by 7% compared to mini grids size for only community load. And this is very important. So what if you can't change the crop mix? What could you do? The next option would be to maintain your crop mix, but also implement bimodal cropping. Now, in 2 out of the 3 case study sites, this lowered the LCE below mini grids for only residential loads. This is particularly relevant for Tanzania, where some regions do bimodal cropping because they experience rainfall twice a year. However, because of climate change and less rainfall and drought, these regions are now seeing only 1 rainfall season during the year. So what do all these results tell us? First of all, you can incorporate irrigation loads into mini grids that will increase the financial viability, but it requires very specific conditions. Therefore, recommendations to both policymakers and developers include promoting bimodal cropping and also irrigation schemes alongside rural electrification plans to increase their viability. Another option would be to allow the adoption of flexible tariffs to enable load coordination. Finally, I will pass on to my colleagues that will talk about the integrated timing planning for Zambia. Thank you.
Hi everyone, I will be presenting my work on modeling Zambia's climate-linked energy and water system, also known as CLUES. This research includes SDGs such as zero hunger, climate adaptation, water access, or energy security. So Zambia has already been feeling the effects of climate change with more frequent droughts. This has caused 2 main problems. 1, food insecurity, and 2, power outages, as 83% of Zambia's electricity comes from hydropower. At the same time, it has set climate targets, such as reducing deforestation, while aiming to become a prosperous middle-income country by 2030. So integrated planning will be key, and this is what this research hopefully helps doing. So let's quickly run through what the CLUES model includes. Water comes in the system as precipitation and can be used by power plants, especially hydropower, industries, cities, and by irrigation. Land is used for crops, livestock, and forests, among others. And on the energy side, a mix of technology can provide the electricity supply for the bioethanol industry, the irrigation, and national demand. So the main questions that this study aimed to address were: how can we build a reliable energy mix that can handle droughts? How can irrigation help? What crops are best for Zambia? How can we make forest conservation policies work? And finally, is the national bioethanol industry feasible for Zambia? So the model was created using a cost linear optimization tool called Osmosis. I studied 3 scenarios on top of a reference case. 1 with drought starting in 2030, 1 focusing on forest conservation policies, and 1 with a different diet. All were studied under the representative concentration pathway 4.5. And today I will be focusing on the drought scenario. So how do droughts affect the water balance? In Zambia, not only does it mean that the country experiences less rainfall, but also higher temperatures. So more water is lost to the atmosphere. It also means that rain-fed crops will yield less and irrigated crops will need more water to maintain production levels. Now let's look at some of the results from the drought scenario to answer the questions I mentioned earlier. So hydropower, as you can see, decreases significantly under drought conditions compared to normal conditions. So this needs to be anticipated when planning the energy mix. Also, we can notice that some plants are more likely to stop running. Why? Two reasons. Either it's because they use more water for the same power output, such as Victoria 4, or it's because they lose more water to evaporation during storage, like Italy or Luxembourg. Smaller hydropower plants tend to suffer less from those and should be prioritized. Now let's switch to irrigation. Three things. One, we've just seen that hydropower plants are in this scenario are at their lowest, but irrigation are at their highest, which means that water usage for crop is a priority. Two, increasing irrigation helps cropland take up less space, which is especially important in the case of forest conservation. And three, irrigation makes agriculture more resilient to climate change. Indeed, if we look at the yield decrease in 2040 and 2060 under RCP 4.5, the impact on land usage is minimal in 2060 when irrigation is more widely adopted. Now let me wrap up by answering some of the other questions I mentioned before very quickly. Land-based diets should focus more on crops that use less water and, if possible, have lower evapotranspiration rates before adding some diversity. Integrating a study like Adis just presented could help answer this question more thoroughly. If Zambia were to meet their deforestation goals, implementing practices that combine livestock and agroforestry will be needed. Three, the power mix will rely a lot more on solar PV and wind energy, and also on storage technologies, especially during droughts. And four, a bioethanol industry nationally could be developed, and sugarcane shows promise as a crop, but more detailed economic research needs to be done before that. Thanks for listening. We've heard enough about water, now to far more interesting elements, fire.
Thank you, Helen. Hi, my name is Auriane, and before we get started, I just wanted to share some pictures with you. This is Thomas Fire, a fire that occurred in California in 2017. Next year, Camp Fire, known today as one of the worst wildfires ever occurred in human history and burnt a whole city by itself. The year after, again, King Fire. So these three events that occurred 3 years in a row in California have one thing in common. If you were here this morning, you may know the answer. They've all been caused by power line. Indeed, power line failure can lead to the ejection of hot metal particles from the conductor that can then ignite the vegetation in the surroundings. This results in often terrible wildfires, especially in regions like California. Thus, in this context, I proposed a model able to predict the at-risk zone area around a power line in terms of fire. So first, to give you a bit of context, why is California in particular subject to this fire? Well, it can be explained by two main things: aging power lines and favorable weather conditions for fire to slowly spread, such as strong winds, dry vegetation, warm weather. On top of that, there is a clear lack of understanding of the mechanism of vegetation ignition by power lines, which explains why proper preventive solutions haven't been identified yet. To tackle this issue, I built a model able to predict the wildfire at-risk area around the power line, or in other words, where is the fire likely to start when the particles are ejected. So to do this, the model was built with the following methodology. So first, the particle trajectory once ejected was modeled on Python using standard equation of motions. So typically particles are ejected when conductors clash due to high winds or when a fault causes the line to arc. The trajectory of particle is directly influenced by the particle ejection speed and direction, but also by the wind, which is why these three parameters are implemented as variables in the model. This gives us the map of the potential landing points on which particle can land. And for each of these points, the model looks at the vegetation characteristics using dynamic maps. Then the vegetation ignition a phenomena or model on a tool called GPyro using equations of heat transfer, which gives in the end the probability that the vegetation will ignite if a particle falls on it. The combination of the landing points and this probability provides the final output of the model, which is a map generated on QGIS, which is basically the at-risk area I was mentioning before. The model was tested through a study of a line located in the county of Ventura in California. So this was done by assuming that a random point on the line was undergoing an arcing event, which is represented here by the red star. And it was done using weather data gathered from official US databases from 2023. So each point represents potential landing points, and the color of the points is associated to the probability of ignition. This allowed to show that the model is indeed able to predict the wildfire at-risk area for a given set of input parameters, and it also shows opportunities of integrating this model in vegetation clearance strategies or in fire spread model. Indeed, if you run the model for different power lines, you are able to lead vegetation clearance programs that are optimized and that targets the most at-risk zones. And finally, the model was also used to assess the effect of climate change on the wildfire risks. So this was done by doing a simulation of the year 2100 and by taking a prediction of the IPCC, which predicts stronger winds, a drier vegetation, and a warmer weather, which gives the map you can see here on the right. So compared to the baseline scenario, the at-risk area is more than 3 times wider, and the particles can travel twice as far. There is an urgent need to create models like this one to better monitor power lines in order to reduce biohazard while accounting for climate change. The key takeaway that I want you to remember is that wildfires are going to get worse with time, but they're not a fatality. We humans are the ones who built these power lines, so we have the power to manage them and reduce the risk of wildfire. Thank you for your attention, and now I'll hand on to Sofia for the conclusions.
Thank you, Auriane. As we have heard, Thank you. As we have heard throughout our presentation, the energy transition requires our joint efforts to tackle. Okay. To tackle adequately the effects of climate change. Current technologies like lithium batteries, oil, and power lines need to address the environmental and social challenges faced. On the other hand, it is extremely important to understand the context and needs of low-income countries to develop a just energy transition. Thank you for your attention, and we're going to open the floor for questions now.
I would like to ask a small question on the model GPyro. I would like to know if you could briefly elucidate a few key points on the physical and chemical submodels that it includes and what type of phenomena it can capture and what it can't.
Okay, I'm going to try to keep it simple for the rest of the people listening. So basically, GPyro is a tool that is going to run physical equations for you when you give it to it. So I modeled this phenomenon using 3 chemical equations, which is first the drying of the vegetation, so evaporation of water. Second was the pyrolysis equation, and then last one was what is called char oxidation, which is basically the phenomenon of smoldering, aka combustion without flame, or very technical term, but yeah.
Thank you.
Any other question?